In this video, we're going to discuss convolution. In particular, we'll talk about what convolution is. And just a note, we're going to go over the square version. And if you understand this section, it should take you no time to apply it to the rectangular version. We'll go over how to determine the size of the output and the stride parameter. Finally, we'll talk about zero padding. So let's ask the question, what is convolution? So let's say we have two images. And if you look closely, these two images are identical, except one is slightly shifted. Let's see what happens when we convert the first image to a vector. So here's the image as a 12-dimensional vector, and the gray locations represent the areas where the intensity values are high. Now let's see what happens when we convert the second image to a vector. And as you can see, the intensity values are in a totally different location. And that's because the relationship between the pixels is more important than the actual location of the pixels. So one thing that convolution does is it preserves the spatial relationship. And there's a few other reasons that we're not going to get into. And let's do one more example. So let's look at concatenate this image to a vector. And it's the exact same as before. And this image is slightly shifted. And again, the intensity values are in two totally different locations. So basically what we're going to do is we're going to take the image, and then we're going to take something called a kernel. We're going to perform convolution, and we're going to get an activation map. So as you recall, we have a linear equation. This can be even a vector or a matrix, and we have the output z. Convolution is analogous to this, and our output will be another matrix. And then we have parameters, and the parameter w will be known as a kernel, and the parameter b will be known as a bias. And this operation will be known as a convolution. So there is actually an analytical expression for that, but it's a little confusing. So let's just go over an example to understand what's going on. So in PyTorch, we can create a convolution object as follows. And for now, we're just going to stick to the case where we have one input channel and one output channel, and a kernel size of 3. And we'll create our own image. And this will represent the number of images in our tensor. And this will represent the number of channels. Only discussing grayscale images, it will be set to 1. Later on, we'll do some color images, but you won't have to worry because we'll be using pre-trained models. So let's see our image in our convolution kernel. And then we'll see the output. So here's our image, and here's our kernel. And just to note, PyTorch randomly initializes the kernel parameters, like the linear parameters. So in the lab, we give them some nice values. So let's go over the operation of convolution. So here's the image, and what we'll do is we'll start off in the top right corner of the image. And we'll overlay the kernel with that region of the image, and we'll multiply every element of the image by the corresponding element of the kernel. So for the first row, we'll get the following operation. So we'll multiply the intensity value of the image is 0, and the first element of the kernel is 1. And we'll multiply those two values together. And then we'll add the second element over here, which is 0 multiplied by 0, and then the third element, which is over here. So then what we'll do is we'll do the exact same thing for the next row. And we'll multiply the first element of the kernel, which is 2, by the first element of the image. And we'll do it for the second column and third column. Add it to our initial value. And we'll repeat the steps till we get to the end of the kernel. And we'll basically add them all together. And we'll get the first element of the activation map. We'll shift the kernel one column and perform the exact same operation, multiplying every element of the kernel by the corresponding intensity value of the image, adding them all together, and repeating it for each row. It's helpful to think of it as a dot product. We'll add up all those values, and we'll get the second intensity value. And we'll keep on repeating the process until we get to the end of the image. And then all we'll do is we'll start at the first column of the image, and we'll shift down a row. And we'll repeat the process till we get to the end of the image. Then once we reach the end of the image, we'll shift down one row and start off at the first column, and repeat the process till we reach the final column, and that's it. So we have our activation map Z. So let's see how to determine the size of our activation map. So let's start off with a 4x4 image, and we'll use the variable m to denote the size of the image. And let's start off with a 2x2 kernel, and we'll use k to denote the size of the kernel. We'll set it equal to 2. So we know that for the first iteration, we're going to have one element in our activation map. We have to see how many units we have left to shift. So we look at this number, and because our image is m and our kernel is k, m minus k pixels or steps. So that means there's 2 more steps. So our final output is just two steps, or m minus k plus 1, which equals 3. So let's verify that. We shift once, we shift twice, and we get to the end. And the same argument can be made for the vertical jumps. So we start all over, we continue to the end, and then we get to the last vertical jump. And we see our activation map is 3x3. Another important parameter in convolution is stride. So the stride is basically the jump. So we have a stride of 1, and we just move once. So when we create our convolution object in the constructor, we have the variable stride. And let's see what happens when we set it equal to 2. So we have a stride of 2, so we have 2 jumps. And then vertically, we have 2 jumps until we get to the end. Now let's see what happens, how to determine the size of the output with a stride value of 2, or in general. So for the first stride, we have 1, and we have m minus k samples left. And because our stride number is larger, we'll have less jumps. And we can get the actual number by dividing the remaining number of pixels by the actual stride size. So here's the formula we use. And doing the math, the size of our activation map will be 2. And we can confirm that by just going through the operations as we did before. So let's see what happens when we have a stride of 3. We have one stride, and we plug it into the equation, we get a non-integer value. And basically this means we're going to get some non-statistical value that doesn't really make sense. So to solve this, there's several ways, and we're going to go over zero padding. So we create a convolution object, and we add in the parameter padding, we set equal to 1. What this does is add 2 additional rows of zeros and 2 additional columns of zeros. And the new size of the image, which we'll denote by m prime, is simply the old image plus 2 times the size of the padding elements added. And we can simply perform convolution given the stride of 2. And that's it.